I'm going to draw here is a plane. Hold on, change my mind. There's a wing.
Oh, that's all fine.
And obviously, if he was to jump out of this, it would probably end badly. But here is our skydiver. Okay, could you please draw your skydiver?
Do we have to draw the plane? I'm not drawing the plane.
You don't have to draw. Well, draw him at equilibrium. Okay. Now I'm just going to label various parts of his journey, Noah, Daniel. At the start, we could say he's in equilibrium. Okay, he's not accelerating. He might be traveling to the left at hundreds of kilometers per hour, but we're not really too concerned. Okay, and I'm just going to finish this awesome. Oh, I stuffed it up. I was never good at drawing planes.
I don't think anyone's good at drawing planes.
There we go.
It's like a predator drone.
All right. Now, the skydiver is going to jump out, and when he does, the half the plane comes with him. No. There we go. All right. All right. Now, the instant that he jumps out, he's not traveling very fast downwards. In the vertical plane, he has zero velocity at the start. And so the only force acting when instant that he jumps out is that of gravity. Now we could say that Newton's second law is that his acceleration would be the sum of all forces divided by the mass, which we could write mg over m, and in that equation the masses cancel, and his initial acceleration is that of gravity. So at the start, he will be accelerating downwards at 9.8 meters per second. However, this is the next statement that I want you to consider. As he gets faster, he's moving through a fluid that contains matter, and matter has inertia. You've got to push it out of the way. To push it out of the way, you've got to exert an action force. And Newton's third law says that there would be a reaction force in the opposing direction. So the air, not only does he push the air downwards, the air pushes him upwards. And that upwards force is called air resistance. And it should make sense to you, because you are all smart students, that the faster you move through a fluid, you are hitting more atoms with greater force. And so your air resistance is directly proportional. I think it's proportional to the square of the velocity. We'll need to check that. We'll check that on the internet. And you will, because this might form the basis of your investigation at the start of next term. So as he gets faster, what I want you to imagine is a little upwards arrow forming. Okay? So what's going to happen is that the unbalanced force is going to reduce. So let's just go scenario 3. I'm going to draw him again. The weight force, remember, always acts. The turbine engine can come too. But I want you to imagine a smaller air resistance. So he's at a certain speed, which produces an upwards force. However, he's still accelerating. But now we can't make this initial statement, because the unbalanced force is no longer weight, it's something a little bit smaller, and so the acceleration is a little bit less than 9.8. So he's getting faster. And he gets faster, and this starts to grow. Still, there's an unbalanced force downwards. Eventually, he reaches a speed, or in fact a velocity, where the upwards force balances the weight force. And again, he is thrust into equilibrium at a certain velocity. We call that the terminal velocity. Okay? The terminal velocity is the speed you are traveling at through a fluid so that the air resistance is equal and opposite to the weight force. And theoretically, you cannot get any faster. Because if you were to go faster, the air resistance would increase, and then there would be an unbalanced upwards force, and you would actually slow back down again. Okay? Now, for a human, for most skydivers, it's about 200 kilometers per hour, or about 35 meters per second. But it depends on a number of factors. The skydiver, if they want to speed up, they could go into a pin drop. And you might see this sometime in videos when people are skydiving. If you change your cross-sectional area relative to your motion, if you reduce it. So if you're out like this, splayed out, you've got a very large surface area. Okay? And then if you go into a pin drop, you've got a very small surface area. That can also affect your air resistance. Okay? And then you can get wingsuits with the flaps here and between your legs, and then you can sort of glide along at a different angle. What I want us to plot on these graphs, I don't know why I've got 3 graphs. Let's plot his acceleration on this first one. And in fact, it's the magnitude of the acceleration because it's in the positive over time. So we know that it starts off at 9.8, and I'm not really sure of the shape that we're going to get, but it's going to eventually go to 0. Okay? For his speed, he's going to start off with a high gradient, and then it's eventually going to top out subscript t. The position time graph is a lot more difficult. S versus t. You're going to start off not moving, you move really, really fast. Well, you're going to get like a quadratic that then goes to a straight line once you've reached your terminal velocity. Okay. Now again, these graphs, you can't model them with a nice, easy v equals u plus at, or s equals ut plus a half at squared, because that's only if the acceleration is constant. What we've got now is that the acceleration is not constant, it depends on the velocity. It's called a differential equation, where changing one thing influences another, which influences the first thing. Okay, so you can get these differential equations. They're a little bit nastier, and they're not even really taught at high school, they're taught at university. Okay, much, much beyond the scope of our class today. Okay, in just a moment, I'm going to get you to determine the terminal velocity of a cupcake. Oh no, I'm gravely serious. Our cupcakes here, we're going to assume, we could all do a mass investigation here because all of these cupcakes are pretty much the same style. They should have the same mass. They should have the same cross-sectional area. They have the same drag coefficient, which is a special value assigned to its shape. And they're all falling through the same density. Oh, what just happened there? They're all falling through the same density of air. Okay? So we might come back in about 10 minutes and we could average our values and find out what the terminal velocity of one cupcake is. Now, what you're going to do is you are going to video physics it. In just a moment, here's our cupcake. You're going to... Cupcake, patty pan, whatever it's called. You're going to hold it at a certain height, and then you're going... It's forced perspective. He's holding it in front. It's then going to fall... Oh, I see. Hilarious. He's looking at his watch. No, he's not. He's looking at his iPad. No, he's not, because the iPad's not going to be in his hand. You're just basically going to allow it to fall. Okay? Please remember that you need to have a reference in your video, and the action needs to be at the same distance. So you're going to basically hold your cupcake in the same line, and you're just going to let it drop. Now, if it wobbles If it wobbles, then what it's doing is it's changing its cross-sectional area. So obviously, we want it to remain in its orientation. If it wobbles like that, then all of a sudden the cross-sectional area has changed, and that will reduce air resistance. So we want to try and drop it as perfectly as possible. Okay, so try your best to just let it drop, and it will wobble slightly, but hopefully we can come to an agreement on what the terminal velocity of a cupcake is. So I would suggest in just a moment groups of two. You have two iPads, one person, or you can swap that. You film the cupcake and then you swap roles. I'm going to get the rulers. Basically, what I want you guys to do is to plot the motion of the cupcake. Now, here's the thing. Don't plot it while it's in your hand. Only start plotting it while it's falling, and then you can finish plotting it when it hits the ground. So you are going to get this shape, which we are then going to analyze when we sit back down. Okay? So, please do that, and we've got 5